So let's try to finish today everything about the theory of ARIMA processes so that we can do some applications maybe already today. On Monday, there is no lessons. Check the schedule. So we see each other on Friday. And if you take my, I mean, not now in general, if you take my book on page 43, I put down like a flow chart on how ARIMA modeling works, at least for a human being, and actually also for a machine. I would write an algorithm for a machine using this reasoning. This is, I would say, my interpretation of what's usually called the Box-Cox method, or for ARIMA the Box and Jenkins method for ARIMA identification. The box is the same box, which is now he's dead. I think he just died a couple of years ago, like 90 and something years old. So a really prolific statistician. And actually, the funny thing, I don't know if it's funny, but he had at the beginning it was just Box and Jenkins' book back in the 70s, and then they made a new version, probably the beginning of the 90s, with the multivariate parts, which was missing at that time. And so this other guy called Reinser joined. But I think Jenkins was already dead in the 80s, and then Reinser also died. And Box, who was the oldest of the three, actually kept on living for many, many years more than the other two guys. But anyway. This is, so I don't know if this is the Box Jenkins algorithm or method for ARIMA identification. At least it's my interpretation of it. Okay, so as I told you, if you're a human being, so you start by plotting the time series, and usually you already see by looking at the plot that if the variance is constant or not. And if it's not, we discussed like a range of so-called variance stabilizing transformations, or the Box-Cox transformation, of which the log is particularly interesting because of the interpretation we can give to a log transform data. Okay, and so if the variance is not constant and there is a relationship with the mean, then usually you can apply one of the Box-Cox transformations to make that decently variance stationary. Okay, I've shown you in that application. I'm still building for a project, but you can already use it. I put the link to this morning on the e-learning, so you can play a little bit with the transformations. And the idea, I think I showed you that. The idea is that there should not be a strong relationship between the level of the time series and the variance. So the best transformation is the one that solves that dependence between mean and variance problem. Then the second question I would ask myself, I do ask myself when I see a time series, is there a seasonality? Because if there is a seasonality, as I told you, in real-time series, seasonality means that it's not stationary mean, because, for example, a given month has a different expected value than another month. And so the mean is not constant. And if it's seasonal, you can take the seasonal difference, and usually you get rid of that feature. When I say you get rid, yes, you get rid of that because of the ARMA modeling, stationary ARMA modeling part, but it doesn't mean that you throw that away, because once you want to produce the forecast, all these transformations have to be reversed, okay? So actually, it's part of the modeling. It's not just eliminating a feature, because then you have to reintroduce that feature. So if the feature is there, you did the right thing to forecast. If you did the wrong thing, you're introducing probably spurious components in the time series, like trends when there is no trend, or seasonalities where there is no seasonality. So it's not something you should just say, okay, if I have summed up, let's suppose there is a seasonality and I take the seasonal difference. That has consequences on the prediction. And actually that part, so the part that is previous to the ARMA modeling part, is the most important, in particular for mid to long range predictions. So very short predictions, of course, the stationary part, so the ARMA part of the model is important. But as soon as you go for, I don't know, h steps ahead with h, which is not just 1, 2, or 3, it's larger than that, then the dominant part of the prediction is the choice you made about transformations, like Box-Cox transformations, and the seasonal part. Here, I'm assuming there is only one seasonal component. Of course, we have then to deal also with the problem of having multiple seasonal components, okay? We will deal with that problem later. Let's assume that for now, we just have one seasonal component. Okay, I take the seasonal difference at the right seasonal frequency or seasonal period. Then, again, I plot, of course, every time I ask myself this question, it means that I do a new plot. Actually, I should have put somewhere plot time series again, but it's always there, okay? Every time you do something, then you plot the time series again. And of course, you can also plot the ACF and PACF functions, but before having a stationary time series, can be beneficial, can give you some clue, but usually, yeah, you do that when you think it's stationary. So after taking off a trend, seasonal component, as I told you, the seasonal difference has inside also the non-seasonal difference. I can show you how we can decompose the seasonal difference operator, and by decomposing that, like factorizing that, again, using some kind of polynomial factorization, I can show you that actually the non-seasonal difference is within the seasonal difference. So you are actually also taking already one non-seasonal difference. Actually, I can tell you that taking a seasonal difference is equivalent to summing up your time series over 1 year and then taking a difference. Okay, a simple difference. It's very simple to prove that. But anyway, so you may have already killed an eventual trend which is present in your data, but you also may have not. There may have, I mean, even after seasonal differentiation or also simple differentiation, there could be the need for a second differentiation. As I told you, real data usually are either stationary, I1 or I2, okay? So up to 2 differentiations is fine, it's not strange. And so you may want to check if after taking the seasonal differentiation, maybe you still need another one. In case you need another differentiation, it will be a simple difference, okay? Because you already killed the seasonality. When I say killed, I would say you already killed the non-stationary part of the seasonal component by taking this difference, okay? So the next difference, if you need it, because maybe it's already stationary, your time series, so you ask yourself, is it stationary, or otherwise said, is there a stochastic trend? So if the answer is yes, so if it's not stationary, after taking this difference, you may want to take another difference. If it's stationary, then, well, you finish with this question. But again, you may have taken maybe your time series is not seasonal, you have not taken a first difference, and you see the same question comes again here. So is there a stochastic trend? Yes, I take the difference. Still a stochastic trend, because you may have 2 differences, and say, okay, if yes, I take another difference. If no, I just assume that I made my time series reasonably stationary, And that's the point where I start working with ACF and PACF, so autocorrelation, partial autocorrelation function, to try to identify the P and the Q values of the ARIMA model, okay? And again, here, you have like some kind of a recursion, because usually you look at those autocorrelation and partial autocorrelation function, the estimated ones, and then you you estimate a model. Well, yeah, of course, you may already have a white noise process, meaning that you may have killed everything just by taking the transformation. So this is meaningful. So you go from, you look at the ACF and PACF function, and then you ask yourself, is it a white noise? Because maybe it's already white noise. In that case, end of the game, okay? Now you can use your model for prediction. Even if it's white noise, all the other transformation have something to tell as far as prediction, okay? So even if it's white noise after the transformation, you are still predicting with something better than a white noise, because there are the transformation that you have to reverse that will produce some kind of non-constant prediction, okay? But if it's not white noise, then you try to identify from this ACF and PACF a tentative ARMA model. So the E we already dealt with, so here's just ARMA. And usually, as I told you last time, but we'll do a lot of exercise about that, you may recognize maybe a dominant AR or MA part or seasonal or non-seasonal parts in the model. Okay, fine. Build a model for what you have seen in the ACF and PACF, and then estimate that model. Every time you estimate a model, you get the so-called residuals. What are the residuals? They are just the one-step ahead prediction error. So you will, we didn't look at the building the likelihood function of the ARIMA model, but you may think it as some kind of minimization of the square error between the original time series, YT, and the one-step ahead prediction, right? So the residual is just the error you make by predicting one step ahead for every time point t of the time series, okay? So you have a time series of prediction errors or residuals, or we can also call it innovation. The meaning of innovation is the part of the time series that you are not able to predict, because it's an innovation. It's the new part. Some part you can predict, some part you cannot predict. The part you cannot predict, it's called innovation. And if it's one step ahead in prediction, then the innovation is prediction error, okay? So you compute those residuals and go back to look at the autocorrelation function and partial autocorrelation function of these residuals. If they're white, again, end of the game. It means you have dealt with the non-stationary part, also with the stationary parts. Everything that is left is just white noise. The white noise doesn't allow you to improve your prediction in any way. And so you can use the model for prediction. Otherwise, you may recognize other patterns in the ACF and PACF. In that case, you add the missing parts of your ARMA models in the model, and you estimate it again, and you compute the residual again, and check the ACF and PACF again, okay? And you go ahead until you have a decent white noise looking ACF, PACF. Sometimes it will be easy to achieve that white noise property. Sometimes if you have very like high frequency data with complicated seasonalities and maybe some form of heteroscedasticity that you cannot eliminate just by using some box-cut transformation. Well, in that case, sometimes you come close to have some white noise-like looking autocorrelation, but I mean, it's just models. It's not the reality. The reality is an approximation. I mean, the model is just an approximation to reality. We do our best, and more than that, we cannot do, okay? So that's basically what you do while ARIMA modeling, okay? So, but something is still missing. I just wanted to give you like the whole picture of what we are about to do using a real-time series. But we are still missing some details in the pictures. I told you how the ACF and PACF look like for an autoregressive process, how they look like for a moving average processes, but I didn't show you how they look like for the seasonal version of them, and especially for the mixture of a seasonal and non-seasonal ARMA process. We check that now out, and then we are able to start modeling. Sometimes things will be unclear. When things are not clear, maybe you can kind of build a larger model than you should, and then maybe test if some of the coefficients may be eliminated, for example. So you go from like a general to specific. You say, okay, I really don't understand if it's better if I put a seasonal AR or a moving average AR. I put both of them and I see which one seems to survive, for example, the testing. Or I can just produce both of them and then compare according to some information criterion. Don't think that there is just a good model. There could be more than one good ARIMA model. What do I mean by a good model? A model that in some way passes all the diagnostic checks, especially on the autocorrelation function. We may follow two different paths, find white noise at the end of the modeling. Both models seems to fit well the data, and which one do we have to pick? Well, the ultimate answer is just use both and then see in the realization of the future observations which one tend to prevail. Of course, we can fake that by using some form of cross-validation, like starting in the middle of the time series and adding one observation at a time, and every time fitting again and predicting again, for example. That could be a strategy. But anyway, don't think that you come up with just one model. Sometimes you come up with 2 or 3 models, and then eventually you decide which one seems to work better as a forecasting model, okay? So let's go back to the seasonal models, which I introduced last time. Last time we kind of gave the whole picture of a non-seasonal, seasonal ARIMA model, which is this one here. And of course, we are still missing another part, which is the additional regressors part, because of course we can use also regressors into an ARIMA model. Such a model is called a Remax model, and we'll add that later. Okay, so how does the ACF and the PSCF of a seasonal ARMA work or look like? Here's the answer. I don't know. Did I tell you already how it looks? I think so. So let's take for example seasonal model, seasonal autoregressive model of order P, a purely one, so we already know it's okay. We may have a constant. P is actually large, so I should. So this is the model. It's just like an autoregressive process where I skip some intermediate coefficients. And the autocorrelation function and the partial autocorrelation function, they look like this. So the autocorrelation function, let's take, for example, s equal to 4, so a quarterly time series, so I don't have to write too long examples. The autocorrelation function of a purely seasonal autoregressive process is 0 for log 1, for log 2, for log 3. Then log S, which is 4 here, shows up. And then we have again zeros for log 5, 6, 7, and then log 8 come up, but lower. And so on until it disappears, okay? So it behaves just like the other, the non-seasonal counterpart, but everything happens on the multiple of the seasonal periodicity, okay? So it goes to 0 gradually, but on multiple of the seasonal period. What about the PACF function? Well, you can imagine that it's just the same thing, but so you have like just suppose we have a seasonal autoregressive process of order 2 in this, which is quarterly, when then the first and the second seasonal delay come out, but then all the rest is 0. Okay? So this would be 4, this would be 8, and here 12 is going to be 0. Boy, I didn't. Anyway. Okay. So it's just the same as the ACF PSF of the non-seasonal one, but everything happens just on the multiple of the seasonal period. So you may want just to isolate by few years ago, when it was more popular to use SPSS, there was a version of the autocorrelation function, the partial autocorrelation function, where the SPSS would just show you the multiple of the seasonal delay, so you could just concentrate on the seasonal part. But anyway, you can do it easily. Okay. What about the seasonal moving average? Well, as in the other case, so as in the seasonal case, the two things just flip around or swap, whatever you want to say it in English. So the ACF, in this case, goes up, it's larger than 0, let's say, or not larger than 0, different than 0. Can be also negative. I just designed everything with positive numbers, but you can also have, of course, negative numbers. 1, 2, 3, 4, 5, 6, 7, 8. So here you get until so the first Q auto correlation on the seasonal legs are different than 0. All the other ones are 0. So okay, and the PSEF, then you have instead the gradual decline towards 0. Again, you may have like opposite signs. It doesn't really matter the signs, but okay, it goes to 0 eventually, gradually. Okay. But anyway, it's very rare that you have more than one seasonal lag. Okay, so usually the Q and the P of the seasonal part are at either 0 or 1. It's very rare. More than 2 is really rare to observe. So try 0 and 1 and not much more than that. Okay. Of course, when you have the full model, as I told you, everything gets mixed. So the autocorrelation and partial correlation function are more messy. Okay. So as I told you, the strategy is recognize something, the things that is more evident, fit that, so estimate the Riemann model, look at the residuals, and if something else is left, then it will become more evident after taking off the most evident part. Okay, So things that at the first pace, maybe you cannot see, after taking the evident parts off by estimating them in the model, all the other that were not so evident that they become very again dominant with respect, for example, to the white noise part. Okay. So of course we can do this in R, but since I produced that little shiny app, we can save some time and boring things of coding by playing around with that thing. As actually, this is still a work in progress because now I have to give the final version by February, so I have a lot of time. But it's already working, and there's of course I didn't put time series already inside this this dashboard. Which can you see the address, or should I? Can you read it? Then I invite you to reproduce what we do here by coding in R or in Python if you like more Python. Okay. Wait, I can write it here. But it's very small. Okay, I think I gave you some time series to play with, and you find it in the learning. I think in the learning there's like a, yeah, that's this blob where data, code, and everything are mixed up. Here. Okay, for example, we can start with okay, with the Italian industrial production, for example. Okay, Italian production industrial production index. You can download it. Then you can also take the GDP, so the Italian GDP, and maybe you can also download already this load by hour. This is a hourly time series. Or actually electroquant. Electroquant is the same thing, but is more recent. This one is pretty old. It's the same one that I used in the book. This is the more recent version of the same thing. But anyway, they're just exercise. So just download the CSV files that you find here. And let's start by playing around with that. So you can, it's very intuitive, so I don't think I have to explain anything about this dashboard. You go from left to right, and you have to, in this case, we just pick up, for example, the industrial production index. You have to specify which is the column of the date, which actually is automatically well identified in this case, which is the column of the response variable, so the time series you want to predict, which in this case the IPI, so in this industrial production index. You have to specify which is the data frequency, which in this case is monthly, okay? And then you click submit. This is just for making the system recognize the dating, okay? Because of course dates may have many different formats, and we try to, with the help of this information, to be able to interpret most of the dating patterns. Okay. Now you can work with the time series. As I told you, the first question we ask ourselves, well, the first one is about variance. So the first one, I would suggest, of course, you can look at the pure time series and already have some ideas. I have actually a strong idea here because here the time series has a higher level in the first part. Then the financial crisis of 2009 comes, and the industrial production in Italy drops down. Okay, and if you look at just look at the values, the variability here is much higher than here. I mean, here, especially the difference between August and the other months. Okay, so this is already a situation telling you, okay, the level and the variability of the time series are positively correlated. So, but then I taught you can actually build such a plot. This is just the means of every year and the standard deviation of every year. We have 12 observations per year in this case because it's monthly. And here you clearly see a increasing relationship between the two. And actually, he already made some suggestions. So multiplicative in some way is synonymous to you should take the log, okay? And actually, this test I just based on this picture. So there, kind of synonymous. And then you can play around. For example, you just can put the 0 of the log, and this 0 of the log. Okay, still there is some positive correlation, but it's very small. If you look at the range here, it's very small. So, of course, you could use other transformation, and we may also try it. But as I said, actually here, it looks like minus 0.9 would be the best solution. Let's keep that in mind. We can compare different models because, of course, as I told you, we may end up with different models, okay? We don't have to choose one. Then we choose one at the end by comparing predictions, okay? So, for example, the log is always a good choice because of the interpretation of the numbers. But if I look at this plot, maybe even a negative minus 0.9 value of lambda seems to killing more the relationship between the standard deviation and the mean, okay? Of course, actually, if I look at this is bad. This is worse than this. I mean, this is, I think, much better. I mean, still, it looks like we cannot fix 100% of the problem, but anyway, we can keep in mind the two approaches. So 0 or minus 0.9. So the first question we kind of answered, okay? Should I take a transformation? Yes. I'm kind of between 0 and minus 0.9, but okay, we take the transformation. Let's just assume for now that the log is the transformation I want to take. So the second question was, is there a seasonality, a seasonal pattern? Of course there is. Okay. It's very strong. It's August. But and for this, as I told you, I also produced this kind of plot, which is called seasonal plot. It's just a plot where you plot every year in the same scatter plot. So you have the months in this case on the x-axis and the value of the time series on the y-axis. So you see that actually the shape within the year is very similar from year to year. So that suggests that there is a seasonality. If there is no seasonality, this is, of course, random. I mean, the time series can go up, so you may see many lines going up, but there would really not be any parallelism here between these lines, okay? So here there's clearly a seasonal pattern, and of course there's some problem with some data which we know it's the COVID time. Now, if we look at here, it's 2020. Okay. Okay. So solution for this seasonal difference, right? So let's take the seasonal difference, which is here. And you see, with the seasonal difference, we've kind of killed all the seasonality. We get some problems, some outlying lines here because of the COVID. Of course, if you reason about this, the meaning of what we did, we are looking at the yearly increments, annual increments, okay? So of course, if there was a large decrement during especially April of 2020, then the next year will be probably a big increment to go back there. And indeed, you see the decrement here and the increment here, okay? And what's this blue line? The blue line is, the blue line is 2009. Of course, we saw that there was a year that in which the financial crisis hit Italy. So it kind of hit it with a delay because it was mostly in 2008 in the rest of the world. You see that year with respect to the previous year, because we're comparing year to year, I mean, that year we jumped up by it's logarithm, so we can read this as a 30%. So the industrial production decreased by 30% in just one year with respect to the previous year. And then, of course, you don't see it anymore because then we kind of remain there. So there is no negative or positive increment. Well, here there's a slight positive increment, which is 2010. So there is a small reaction on 2010 with respect to the big fall of year 2009, but not that large to get back to the previous level, okay? So try to reason always on the meaning of the data you're looking at, okay? So you can interpret that, okay? Anyway, so this is the time series after the transformation. Of course, we have this big crisis here, and of course, there's the COVID problem here. Of course, with such time series, we have to fix these things later, maybe with some regressors, but I told you that actually regressors are possible in a Riemann model. So maybe we just can skip that part by fitting our models. And then later we will fix this by including features or regressors, whatever you want to call it. But it seems like now we have a reasonably stationary time series, right? So if this is reasonably stationary looking, then we can go to the identification of the autoregression and the partial autoregression, of the ARMA part by looking at the autocorrelation and partial autocorrelation function, which are here. Okay. So autocorrelation, partial autocorrelation. I didn't even write it. It just okay. Maybe I should write it somewhere. No, there is no ACF, PACF. I just gave it for granted that. Yeah, it's there. Okay, so I did. Good. Anyway, so of course there's persistence. So this is not white noise. What we are looking at, it's a persistent time series. We see that there's a relatively long correlation. It goes to zero probably slowly and in a maybe sinusoidal pattern, but eventually it goes from a number which is far away from zero to zero. What about, so this suggests what? Well, this suggests probably there is some kind of autoregressive patterns in our data, right? So the ACF goes to zero gradually, autoregressive, and autoregressive component is there, okay? Yeah, any question?
So the order of the...
Yeah, for the order, it's kind of complicated. Okay, the delay, the first delay is large, so the first lag is very large. So AR1 is, of course, then. Are these large enough? I don't know. We may try to put AR3.
AR2 or AR3.
Yeah, for example. Yeah, as I told you, it's not that clear. And then I'm sure we will see something at the seasonal lags, because seasonality It's true that we killed the non-stationary part of the seasonality, but some seasonal memory is probably still there, but we don't see it because it's something else is dominant. But probably, I see, for example, here, look at 24 comes up. And here is also the largest in this area, okay? And well, 36 and 48 are not there, but as I told you, actually the non-seasonal and the seasonal parts, they interact together. So it's very hard. You see, okay, 36 not that high, but there's 37, which is higher. Again, here I have 24, then I also have some 25. So probably there is still some seasonal autoregressive moving average parts, but they're interacting with the rest of the model. So our approach is, let's just put the mass evident thing, and then let's look how the residual of a model with that part look like. So we may introduce the, for example, autoregressive order tree. Let's try with that. And then decide if we have to put something else. And maybe we can also go back. Maybe we see that an AR2 would be sufficient, so we can go from 3 to 2. And let's see how that happens. For this, you have to go on to the manual modeling part, the automatic modeling part, which actually is the one that I haven't written. I have to integrate better with the rest. But yeah, okay. Yeah.
What does the shape of the ACF in this case mean?
Yes. Could be here. So what we notice is that the autocorrelation function is going to 0 in a gradual way, maybe even moving up and down. But anyway, it starts large and it goes towards 0. Okay. What about, so that suggests already an autoregressive part, because otherwise, if you just have a moving average part, then it cuts after some value and then it becomes 0. It will not be exactly 0. These are sample data and these are same estimations, okay? But so we have just to think about what's close to 0 and not close to 0. I didn't put any bands here around because I could put the confidence interval for testing for that to be 0 or not, but I didn't do that because usually we don't look at the single autocorrelation if it's 0 or not. We look at the at patterns, okay? So that just, I mean, I added, but
I think that the clear fact here is that if we had a moving average after certain lag, we for sure see nothing.
yeah, right. A purely moving average project, this would cut to 0 after a while, okay? But here, it just looks like it goes to 0 in a gradual way, and maybe even sinusoidal way. What about the order of the ARP parts? It's hard. It could be an AR1, but maybe an AR3. Yeah, of course, you say, okay, but this is not much larger than this one. Yeah, you're right. Probably AR1 is better. But we can estimate the AR3 and then go back in case the second and third, like, for example, are not significant, for example. Why not? So and again, in this case, the time series is relatively long, so I can afford also some kind of overparameterization, which then I can get rid of. If I had a very short time series, in this case, I said, no, I just pick AR1 because I cannot afford too many parameters. But anyway, if you look at the e-learning, I think I put there so many sample autocorrelation and partial autocorrelation function. So you can kind of look at these animals and see. Get used to learn what kind of process is generating what kind of autocorrelation function. Yeah, that's because I didn't tell in explicit way. There is a one-to-one mapping between an ARMA model and an autocorrelation function. Okay, so that's why you can go from one to the other one. Okay. Good. Is that clear? So go to manual modeling. We can select the ARIMA class of models. Here it already suggests 0 because I bounded this like initial at least values for the lambda and also the seasonal frequency on previous information. Okay, you can of course change it. Let's start with the log. The log was one of the two choices of our. So we said we want the seasonal difference, which is here. You remember the large D is for the season. Large letters are for seasonal part, and the small letters are for the non-seasonal part. Here we have the autoregressive part, so AAR, the integrated part, so how many difference I need to take, and the MA part. It's just like in, also if you use the same function in R, you get just the same ordering, okay? And just leave include constant there. Okay, what does include constant mean after taking one difference? It means that there may be also some deterministic trend, because remember, after applying a difference, if you leave the constant there or the intercept, whatever, or the mean, whatever you want to call it, it's the mean increment. And a positive mean increment means that you have like also a linear trend. You have a linear trend plus a stochastic trend, okay? So you can leave it there, or maybe if it's not significant, we can also get rid of that. And then we want to put the AR3, we said, let's try with AR3. And as I told you, you could select also regress. So, okay, just this is again taken. I'm just using here the engine here is just the ARIMA function of R. This is all R. Okay, it's made in R. Also in the ARIMA engine and the ARIMA function, you see you have three choices. So this is ML is maximum likelihood estimation. Of course, it's not machine learning. It's maximum likelihood. CSS stands for conditional sum of square. And this is, okay, this is just what kind of estimation. So maximum likelihood should be the best one, especially if you have small samples. If you have larger samples, they are equivalent, okay? But in small samples, maximum likelihood is better than least squares. It will be clearly later what's the difference between, it's not a great difference, but there is some difference here. I tell you, you will see later, because we will understand better that when we look at the model in state space form, okay? So wait a little bit and you will understand what's the difference between these methods. But anyway, from a computational point of view, which is what you're interested in, if you have to do that in the real-time series, CSS is much, much simpler and quicker to estimate, to run on a computer, okay? So if you have many time series or a very long time series, just pick CSS, okay? Least squares. Maximum likelihood may be, especially for long models, if you have large models, maximum likelihood becomes very heavy to estimate, okay? The same holds also in Python, so watch out if you use Python. What's the first choice? This is just because CSS is quick. In that case, the algorithm uses the least square algorithm to get initial value to start a machine learning optimization, okay? So you also have maximum likelihood. So if you have time concerns, use CSS. That's the basic message here. Now we can leave it here because anyway, well, this is maximum likelihood. I wouldn't pick maximum likelihood pure because initial values are worse, so probably this is going to be anyway quicker than pure maximum likelihood. Okay, okay. Here there's also the possibility of selecting a so-called holdout sample. So it's a kind of minimal cross-validation. It's not really cross-validation. We just pick how many observations at the end of the time series we want to leave out, and then we try to predict them. Okay. So maybe in order to maybe get rid of the COVID period, maybe we can just leave, I don't know, maybe I don't remember how long the time series was. So the last observation is, well, it's February 2025. So if you want to get rid of COVID, maybe we can leave 4 years off, or maybe 5 years off. Well, of course, predicting 5 years ahead is pretty complicated. So don't expect great results. So 5 years are 60 observations, right? Yeah. Is that clear? What's this holdout? So I'm just throwing away the last 60 observations. I will train the model on the remaining ones, and we can also see the prediction, but the prediction is the final end of this modeling part. So you can press fit model to data. And again, here you have many things. Here are, let's call it residuals. So these are just the one step ahead prediction errors, okay? And this is the autocorrelation and partial autocorrelation function of the prediction error. So that's exactly what we have to look at, okay? Well, first of all, see the range is a little bit smaller now. It's -2 or -0.2 here. And what we see, what's left here, I don't know, it's not that 100% clear, but for sure we see something at 24, 36. The strange thing is that at lag 12, there is not that much. Usually you have lag 12, which would be much larger. Here we have a large 24 and 36, but not a that large 12. As I told you, in real life, things are not so clear as in example time series, okay? So what should we add? Okay, I tell you one trick. Is something that happens very often when you put a difference. So this is like a rule of the thumb coming from experience, but has also some theoretical grounds. If you put a difference, usually you get the moving average of the same order as the difference. So if you have like a simple difference, you get the non-seasonal moving average part. If you put a seasonal difference, you get the seasonal moving average part. Okay? Is that justified? Looking at this picture is strange because it looks like we both have. Actually, we could put also the seasonal autoregressing and seasonal MA parts, because it looks like they're none of the two is going to 0. Well, probably this is, well, if you look at the 48, it's not large. It's very close to 0, and this is going actually to 0 gradually. So actually, this suggests a moving average part on the seasonal components. This is strange. Usually I should see this peak here, but I see it there. Why is that happening? I really cannot tell you. Well, actually, I didn't get rid. Probably one of the problems is that I really didn't get rid of the COVID. Look, the COVID is here actually. Maybe we should just re-estimate the model. Maybe taking one more year off or a couple of months off, because the COVID is clear here. So maybe let's just re-estimate the model, and we take, I don't know, 64 observations off. I mean, it doesn't change that much. But I mean, the 24, the 36, and the 48 is clearly here. Strange what's happening here. I really cannot explain. This is some way suggesting a moving average part of order 2 on the seasonal part, which is, I just told you, usually you have 0 and 1, but this is actually suggesting actually of order 3. It's a little bit too large, but anyway, let's try to just apply the rule that I just told you. If you take a difference, then put a moving average of the same order and see if that helps. So I just put So the rule of the thumb that I just told you means that if you have one here, you want a one here, okay? Or if you have one here, you want a one here. Okay? So I fit the model again. Yeah, it doesn't get that better. I put also, you know, a seasonal autoregressive model. Let's see if we get some better result. Yeah, I mean, yeah, we are really not able to get rid completely of the seasonal parts. What's my interpretation of that? That probably the seasonal pattern changed a little bit in some way. And actually we saw it. We saw it because here we saw that actually applying any kind of transformation doesn't really fix the fact that here, even if the trend is larger, the level is larger, we cannot fix this heteroscedasticity due to the variance of the seasonal components. I mean, this is probably a complicated time series. It looks like there is one word that ends up here, and there is a new word that starts here. Sometimes you may just want to throw away all the data, which we can do, but not within the maybe I should do that. That you can just choose a window of data, not all the data. But anyway, you can throw it away from the CSV file, so CSV file.
Even because here the window that comes after the new word inside is of 10 years of data from 20.
Yeah, right.
Maybe it's better to cut the data.
Yeah. Yeah, in this case, probably that's another solution. As I told you, sometimes having more data is not really solving problems in time series analysis, because in time series analysis, we exploit the fact that the future in some way is closer to the past, is similar to the past. But if the future, I mean, if the pattern of the time series changes, then the future is not similar to the past. Okay, so, but anyway, let's go on with one model. Maybe we can, yeah, I should add that feature of throwing away observations from the beginning. I will do that. We can do that in R. Let's just try to build a model anyway. But yeah, we have some problems here. It's not a simple time series. And of course, also, yeah, this jump here is also ruining. But anyway, yeah, we can try just to leave this model. It's not a great model, I recognize. This is still large. I could put 5, a p equal to 5. I'm not sure it's going to be much better. Well, somewhat better. But anyway, the message which I told you before is that how good we are at modeling the stationary part affects only the very short-term predictions, right? How good I model the non-stationary parts will affect all predictions. Okay? So that's much more important. So it's better, in my opinion, to have some more scenarios. For example, comparing the lambda equal to 0 with lambda equal to minus 0.9, or adding maybe other. Actually, here there is really no reason to add another difference. But those are the things that really matter when we do predictions, at least mid-range and long-range prediction. What else is here? Here are the forecasts, which actually are not bad at all. Sorry, I think yeah, sorry, when I went back, I didn't notice this got back to 12. Okay, 12 is, that's also why things change a little bit. So I'm actually leaving out just 1 year and not leaving out 60 months. We can try that again. Of course, 60 months are very hard to predict. I mean, this is good. This is a good prediction. And here you have all these loss functions. Some are loss functions, well, there are kinds of loss functions, but actually some are, well, technically they are not really loss functions. So this is the root mean square error, which you know, so it's the roots of the mean square error. This is the mean absolute error, so the mean of the absolute error of the forecast. MAPE is the mean absolute percentage error. And these two are really not loss functions, but they're just the mean of the errors and the mean of the percentage errors. Okay, that tells you if you overshoot or undershoot in your prediction. Here we're clearly overshooting. So if these are a negative, it means we're overshooting. So the real data are black ones, and our prediction is the green one. Okay. Let's try to do this again, but leave like was 64 observations out. Of course, predicting more than 5 years is really not a successful task. Well, actually, we were pretty successful in doing that. I mean, the mean absolute percentage error is 5.6%. I mean, for 6 years of prediction, or five and a half years of prediction is not bad. Of course, we are not able to predict COVID. Nobody was. But it looks like after COVID, things kind of started again to work as before. I mean, the prediction are good, so the pattern, while the financial crisis kind of changed the patterns of the data, and that's why probably we could even leave those out. The COVID actually didn't have that impact on industrial production. Yeah, locally, yes, but in the long run, no. Okay, for example, this is one candidate model, and I said, okay, then we can add that model to some kind. I call this a model portfolio. So we can build this. We can say call it ARIMA 1. This is our first ARIMA. Let's call it ARIMA 1. And now it's stored. We can go on and see other models, but this is stored. I didn't show you also other things, other features we have here. So the estimates, this is just the output of the ARIMA functions in R. It doesn't give you p-values. For some reason, they've decided not to. I don't know why, but anyway, each coefficient is significant at 95% level if it's at least 2 times their standard deviation or standard error. Okay. In this case, for example, the drift is actually not there. The drift is 0. Indeed, there is no drift in the time series is pretty constant. This is a sad story for industrial production. There was a time where it was increasing, but it doesn't happen anymore. So the drift is 0. All the other parameters tend to be significant. Okay, the AR4 maybe and the AR5 are not significant. But there is no way also in R to get rid of some intermediate delays. Maybe there is. I never did that. Maybe by looking at the instruction of the function, there is some tricks to fix those at 0, estimate. But anyway, usually you don't do that. Okay. So these are not significant, but this is significant. So this is significant. No, sorry. Sorry. We can get rid of these 2 because they're AR4, AR5. We can get rid of these 2. This is the seasonal autoaggressive part. This is the seasonal moon range part, and they are significant. So we can re-estimate actually this model, throwing away the AR4, the AR5, and the drift. So, well, just go back here. let's put 3, and constant we can exclude, and that was it. And we can call this ARIMA 1 I don't know, less, but smaller. So I don't know, whatever. And you will see in the portfolio, you see your models and on the prediction performance. Actually, the ARIMA 1, but smaller, is doing slightly worse, okay, on this data, of course. Okay, because if you look at root mean square error in absolute percentage error, okay, and let's try another ARIMA model when we go with the minus 0.9 here, for example. Maybe we can just leave things like this and look at the residuals. Okay, what I did is I took the box Cotes transform that it looked to behave better as far as that plot that I show you at the first place, so the mean standard deviation plot. And then I left, of course, the seasonal difference, but also the AMA. This is, as I told you, this is kind of a rule. You can always, when we put a 1 here, try to put a 1 there as well. So let's look at the autocorrelation and partial autocorrelation function. Again, of course, there is some autocorrelation here. It's clear. Well, now the signal about the first relapse seems to be much stronger. So AR3 would be a good choice. I would estimate just in AR3. And again, it happens, these strange things where we don't see something about on the 12, but we see the 24 and the 36, and here also the 48. But we already have dealt with the moving average seasonal parts, and so all there is left to work on the seasonal part is putting the autoregressive seasonal part here. It's not that typical, but let's try. I mean, it didn't fix this. As I told you, it's probably just because things have changed in time, and maybe making this time series shorter would kind of solve the problem. We can check the forecast. So the forecasts are actually slightly worse than the other ones. What about the estimates? All coefficients seem to be significant. Mm. And then we can add this as I don't know, ARIMA do too. Okay. Later will be, well, here I put some other models. ETS actually we will not see in this course. We'll spend some time on UCM. This is a very simple neural network, just an autoregressive neural network. And Profit is probably you have already heard. It's a model, forecasting model made up by Facebook, which works so. It's very easy to beat. It's not that great. It's good if you have multiple seasonalities. For example, Profit is able to deal with multiple seasonalities. And then, of course, you can do many form. So now we have like 3 models here. Actually, the first one was the best one. What about automatic fitting? As I told you, at the moment, I still have to fix a little bit the fact that this is like a separated part. But if you go on automatic modeling and pick up ARIMA, and of course, select the same holdout sample, so 64. Now, just running the auto ARIMA, which I think we can beat pretty easily. I think we already beat. I never tried it, so it's a surprise to me as well. Of course, it takes some time. So we can. I think it's actually doing similar to our best model, second best model. The problem is that. So it picked AR2. Okay, it takes two differences here. For some reasons, it's very complicated model, 210, 211. And I don't know, let's look at our, so for example, the root mean square error is 8.05. And our, well, actually we get is exactly the same. Yeah, we're slightly better if you look at the mean absolute percentage. Well, they're kind of equivalent. Okay? It's strange that they are so equivalent because the difference here makes a great difference in the. I mean, the fact that there is a second difference here should make the model rather different. And of course, we could. My idea now to what I want to do in this application is just that all the automatic models should be stored into the portfolio, and so you have it there, and you can either just use the automatic ones or also have the manual ones. But we could, for example, enter the same model. So we can store it. So this is 210, 211. And with the log, I guess it's on the log. It doesn't tell, but it's on the log because it's based on our my first testing. So this would be 0, and then it's 2, 1, 1, and 210, 211. Sorry, 64. Yeah, it is. Yeah, it's the second best. We can store it. And then, of course, is you can do ensemble prediction. This is just the average of every possible combination of the models, okay? So the best actually is our first ARIMA together with the auto ARIMA. It provides the, well, actually it doesn't really change much. It's similar to our, actually if we sort by mean absolute percentage error, this is slightly better. Yeah. And actually the bias is a little bit better in our case. we tend to be more mixed above and below than the other. You can actually, you can, for example, sort by and you can see there are like 15 pages here. You can check them. They're ordered, of course, and usually it comes up that mixers of models, so ensemble models, can make better prediction than single ones. This is not a very intelligent way to do prediction. I mean, ensemble models, you can make them in a more intelligent way.
Maybe.
But I mean, the average is good. It's simple and good usually. Meaning that we can kind of optimize something by building ensemble models, but the average is still really good.
It makes more sense if we ensemble really different models.
Yeah, of course. This is more thought for picking up. It's told. Now I have like five different classes of models. Of course, I can add and add. I will expand with the time this stuff. Well, shiny up, but yeah, of course, if you have also like linear and nonlinear models. Well, let's just, for example, go automatic with, I don't know, profit. So we can leave the default. It's fine. The default is fine. This is what Facebook does. Okay, so we can beat Facebook. It's very bad. It's a terrible model. And the forecasts are terrible. Okay. Maybe let's try it with the flat growth. This should improve a little bit. No, it's even worse. As I told you, profit is not really a good thing. Neural network, this is like an autoregressive. This is will be like a non-linear autoregressive model. We will talk about these methods later. You see that it's just you can think of it as autoregressive models, but not linear in the past. And we can also apply some transformation. Default is not transformation because anyway, a nonlinear model is also able to learn also like heteroscedasticity, for example. Okay. And you can pick how many legs and how many seasonal legs. At the end of the day, it's very simple. It's like just like a seasonal, non-seasonal, autoregressive process, but instead of being linear, is non-linear. And I don't know. Let's try to. And you can you can choose the hidden layers, the number of networks to fit, because in neural networks. The network is a way is random because it depends on the starting value you provide to the optimizer, right? And so you can pick many initial different values and then average over that if you want. But just leave it to the minimal because of course that increases the computation time. Just to have a different comparison model. Not very good. Anyway. Yeah, probably we could choose larger number of lags. But anyway, it's in this kind of time series, so monthly, quarterly time series, it's very hard to beat linear models with complex models. Okay? So if you have monthly time series, quarterly time series, even weekly time series, you don't have to bother too much with machine learning. Okay, we will see machine learning on time series where it's meaningful. There's still a lot of memory here. We are not cleaning up the memory of the time series, and the forecasts are bad. Anyway, well, here we really don't have estimates. So, but anyway, of course, then you can forecast and save the prediction, whatever. So this is basically what we do when we do ARIMA models. For example, let's just start all over with another time series, just to do some exercise. So the GDP, so Prodotto Interno Lordo Italiano. Actually, I have also Prodotto Interno Lordo Italiano Dummy. You can pick the. It's just the same time series, but I already built some dummy variables that we can use if you want to adapt that period of the COVID. So you have the GDP, the Italian GDP. So this is, for example, how it is stored the date in this data, in this time series. You have like the year and then the Q for quarter and then the number of quarter. Of course, that has to be converted into some kind of date. Then you have the GDP, and then you have like the dummy, which is the first quarter of 2020, the second quarter of 2020. Of course, it's always 0. It will be 1 just the first quarter of 2020. I didn't show you yet how to put regressors into ARIMA models. Doesn't matter. It can be done, okay? And we will see how to do it.
The X-ARIMA.
Yeah, right. Yeah, if you look at the ARIMA function, there's also the XREG parameter. In the XREG parameter, you can define regressors. And then I'll tell you how the regressor enter the model. But in R and also in Python, the regressors are always thought as if they were in the level of, in the original level of the time series. So if you take the difference, for example, of the time series, the same differences is taken also on the regressor, so that you can also you can always reason on the levels, and because you could eventually say, okay, I first take the transformation of the y and then I apply the regressor. No, in R and also in Python, that is not what happens in most of the softwares. There are some software where the x are used after the transformations, but most of the time the x get the same the same differences as the y's, so you can always reason in terms of levels of the y and on the of the x variables. Okay. Anyway, I'm sorry. First, we have to. Sorry, we have to. It's not monthly, it's quarterly. Submit. So now we have a real date. You can explore the data. Well, this is the time series again. Same story. Financial crisis, COVID. Okay. For some reasons, which I think are related on how the National Statistical Offices build the GDP time series, we don't see any multiplicative type of time series. So it looks like the seasonality, the variability due to seasonality doesn't grow when the time series grows, which is strange. It's kind of irrational. But in my explanation of this fact is that it's just probably because the way the statistical offices build GDP estimate on a quarterly basis. You have to think that full GDP information, okay, full GDP information is never known, but almost full GDP information is known only once per year, okay? Because a lot of accounting are just done once per year. So how do you transform that yearly information into a quarterly transformation? Of course, there are many accountings that are done on a quarter basis. For example, in Italy, I don't know if you know it, if you have some family member that run businesses, you know that you pay the VAT, so the VAT taxes every 3 months. Okay, so there you already are doing some kind of declarations, to some official declaration where you're telling how much you earn in the first 3 months, in the second 3 months, and so on. So this the quarterly GDP is always an estimate. Of course, also the yearly GDP is an estimate, but the yearly GDP is an estimate based on much larger pieces of information. And the quarterly GDP is based on approximation of what you can see that you think can approximate the rest of the economy, okay? So when I see that the variability of the seasonal variation of a GDP doesn't multiply, but just sum up so it's additive, it's not multiplicative. I think that they're doing probably decent work, but not a good work in official offices, because it's not very rational. The seasonal variation should be in some way proportional to the GDP. It shouldn't add to the GDP. But that's how it is. It's not that way also only in Italy, also in many other countries. You see, probably just use the same techniques. It's not a simple task to build these numbers. It's just as a disclaimer for the people that has to do that. It's not simple. But anyway, that's strange, okay? That's a strange thing. So you see, there is no suggestion it's multiplicative. So actually, the mean standard deviation plot, yeah, okay, is slightly decreasing, but I wouldn't bother too much with that, okay? Probably we should take no transformation. Seasonal plots. Well, of course, it's a seasonal time series. Again, August is now here. Winter vacations are here. So it's not as strong as a seasonal time as a monthly time series, but you clearly see the seasonal pattern. So a seasonal difference we have to take. I didn't show you one feature here, the seasonality. It's kind of. I wanted to show you this one. I didn't explain you what a spectrum is, okay? Usually I don't do it, but I put it here. You may think of a time series. So you're more on the direction statistics than mathematics. So this is the best and I would say the simplest way and less time-consuming way to explain what this object here is to statisticians. We already regressed a time series on cosine and sine function, right? You remember, we did that in order to model the seasonal patterns, okay? And I told you, you have to build sine and cosine at this frequency. The frequency was 2 pi divided by s, and then you have times j and t, and j goes from 1 to s divided by 2. Okay, this is the same thing, but you want to fit the time series on all sinusoids you can fit, which are, at least the most interesting set of sinusoids you can fit to a time series is at frequency 2 pi divided by n, where n is the length of a time series, times t and time j, and this time j goes from 1 to n divided by 2. So you have exactly as many regressors as observations in this case. So you really don't have an error. You have no estimation error anymore. You are fitting exactly the time series to the sinusoid. And then you take the coefficients of the sinusoids at the same frequency. You take the square and plot it here. What you're doing, you are just dividing the variance of the time series into the variance due to different cosine and sine function at these different frequencies, okay? And the nice thing is that we can recognize seasonalities very quickly. For example, here we have a quarterly time series, okay? So a quarterly time series, if you remember, has 2 seasonal frequencies. One is this one, and the other one is this one. Okay, so this is just equal to pi divided by 2, and this is just equal by 2 pi, okay? Okay, leave here in the plot, this is always times pi, okay? I didn't put pi there. Actually, this is half pi, okay? It's just the way you plot usually this kind of plot. So the range is from 0 to half pi. So the pi I just threw away, so it's half, okay? So since it's in half pi, we have to divide this by 2, so we went 1/4 and 1/2. Indeed, we have 1/4 and 1/2. And these are the peaks. Okay. This was just a really rough explanation. Maybe I will explain you better what a periodogram is, but in some way you already are able to find seasonalities also by looking here. But this very quick reasoning that I just provided to you. And this fact here means that it's kind of trendy. The fact there is also a peak here, the frequency close to 0 means that there's also kind of trend. Or anyway, a very persistent time series. But anyway, I just gave you this because it's here, this short explanation. Okay, let's go back to our modeling. So we say, okay, seasonal difference we have to take. Is this stationary? Yeah, probably it's stationary. If it's stationary, we can go look at the autocorrelation function and partial autocorrelation function. So let's try to read this. Clearly, again, we do have something autoregressive because this is going to 0. It looks like there's also some kind of sinusoidal behavior, but then eventually it goes to 0. The fact that there is a sinusoidal behavior, if you remember, I already told you that, it means that probably there's something like a business cycle, okay? Something that in some way let the time series go up and down at a certain frequency. In this case, for example, it looks like the length of the frequency is about, I don't know, it's between, I don't know, 13 and 16. 16 is 4 years. The length of a business cycle, yeah, it could be 4 years, so why not? And then the autoregressive part seems to be equal to 1. Now, this is very clear compared to the other one. So we have the first log of the partial autocorrelation function that is large. The others are not so large apart from the seasonal ones that probably are interacting with this one. If you remember, I showed you the AR1 and the seasonal AR1 are interacting. And so we see 1, 4, and 5 out. Okay? And that's exactly what is happening here. Okay? Or also, it can also interact with the AMA part. So what should we model here? Well, here I think it's pretty much clear. AR1, we have to put. We could fit the AR1 and see what happens, and maybe we can do that. But in my head, I already have the idea that probably also a seasonal thing, I have a seasonal thing I have to put, and again, we are taking the seasonal difference, then I'm more for the seasonal AMA parts. But we can also do it in 2 steps. Let's just fit a purely autoregressive model. So we said we want the seasonal difference in AR1. And for now, I don't add anything else. Let's just leave the constant there. Again, I don't know, we can leave some, I don't know, 5 years is 20 observations, right? Maybe let's see if we can leave the COVID out. No, a little bit more, 22 observations. Now the COVID is out. Okay, actually, by putting the AR1, we see a lot of more things going on. Okay, in this case, it's strange because we still see this here. And some are missing. There's something, maybe I left, let's just leave more observation. Maybe I took out too many observations. And doesn't matter the COVID, okay. Yeah, of course, this is dominating, but anyway, now it's clear. Okay, so I went back to a situation which was closer to the first one. Well, this is from the manual, okay? So the autocorrelation function, the first seasonal lag is out. All the other ones are going back to zero in a gradual way. What's that? Doesn't work. Un MA stagionale, MA seasonal. Because, yeah, it's the ACF that is just, so this is really manual ready, so handbook ready. Okay, it looks messy, but if you look at the range, it's really small. Now it goes from minus 0.1 to 0.1.
Can we back at the previous graph?
Which one?
With,
Without this one?
yes.
Yeah, this is extremely clear.
Yes.
Which it is rare that it's so clear. Don't expect to see many of this type of autocorrelation functions. It just doesn't.
So this is an MA4.
Yeah, it's a seasonal MA. No, it's not a seasonal MA with seasonality 4.
Yes.
Because the first autocorrelation, it's first in the seasonal view is out, and the other one are gradually going back to 0 as well.
But if we try to model this with the simply moving average,
you can try, but it will actually nothing will happen. You will not clear anything there. See, well, now this is exactly 0, but it was not a problem.
Yeah,
We didn't
I just
fix
want
that.
to see if things are.
Huh?
I just want.
You could approximate that by using a non-seasonal AR4 MA4.
Exactly.
Okay, yeah, you can do that. You're estimating more parameters, and probably you're doing a worse job. But actually, you see, actually, it's still there. Yeah, it's it just doesn't work. That's why we use the seasonal part because it's usually necessary. And this is much better. As I said, I didn't put the bands. Maybe I should put the bands just to give a little bit of the dimension of these numbers. I will do that. And so this seems to be a reasonable model. We can look at the estimates. Well, in this case, the drift, well, also in this case, the drift is actually not significant. It's not at least twice the standard deviation. So, and again, it's very sad to say that, but our GDP doesn't move much. It stays there. And it's been a long time. And the rest of the coefficients are significant. And what about the prediction? Well, they're great. We're kind of underestimating a little bit in the long run. Indeed, you see the first, so the mean error and the mean percentage error are positive. So you have the mean absolute percentage error is less than 1%. It's very good. One thought reasoning about the use of the mean absolute percentage error. It's probably the most simple to communicate loss function. So if you go to your clients, somebody hire you to make prediction, if you communicate the mean absolute percentage error, it's very simple to understand. So on an average, your error is less than 1%, okay? Is that a good number to select models? Maybe not. Why maybe not? Well, because the means you get the mean, you get the error on the top, and you get the real value on the bottom. So it's a fraction, right? The error is on the top, and the value of the time series on the bottom. Suppose you have a time series which is growing. It means that you are like down weighting a lot the largest values, because it's on the denominator of the fraction, right? Or suppose, for example, you have a heavily seasonal time series like the industrial production. So if you're in August, you're dividing the error you committed by predicting August by a very small number compared to all the other months, right? So it means that error is dominating all other errors. So you're picking the model that actually predicts August the best. Is that really what you want to do? So you have to reason a little bit about the interpretation of the loss functions. Of course, here we have like this standard loss function. As I told you the first lessons, the loss function should be defined by the model. By the problem you want to solve. These are just generic. We don't know what kind of problem I want to solve here, right? But anyway, the mean absolute percentage error is very good if you have to do your presentation and to talk to the firm that hired you for that job, because it's really easy to communicate, but don't use it for model selection. Okay? If you don't have better ideas, root mean square error, or mean absolute error are of course much better. They're like more uniform all over the values of your time series. Okay. For example, yeah, I told you I didn't show you how to put that into the model. We will see that maybe we can conclude with that. The lessons of today, we can try to put the regressor here. Here we have the regressor for the COVID period. Actually, we could select all of them and then just keep the ones that seems to be significant. I didn't say, okay, we can, wait, I save first the model, so we have like, and then I fit this model with all the dummies. Actually, the prediction got a lot worse. And maybe we could throw away also the constant here. Yeah, slightly better. But in the estimate, we can realize which of these dummies are actually significant. For example, the first quarters of 2020 is of course significant because it was the worst one. So the production went down by 30,000 billions. The GP. The second quarter is also significant. Well, there are significant. Well, no, just for example, 2021, sorry. Okay, this one is not significant. All the other ones are, and this one is not significant. All the other ones are significant. So we could just throw away the last two of these dummies. But it looks like for some reason, actually, we're doing worse as far as the forecasts are done. And also the residuals are worse. Maybe here we could increase the number of autoregressive lags on the seasonal part. So I don't know on the seasonal part. There is something here which is strange to. I mean, we already put the MA part. We can try to put the autoregressive part, but it doesn't change. It didn't change. Actually, it seems more complicated to fit it when we take care about the COVID than otherwise. And the prediction, well, the prediction are now somewhat better. So we added this to autoregressive order too. And another suggestion, a model that suppose that you're panicking. You say, okay, I really cannot find any model for this time series. If it's a seasonal time series, a panic model is the so-called airline model, which is the model that Box-Jenkins found on the air passengers time series back in their book. And it's 011,011. So if you're without constants. So, for example, I can say this as a ARIMA 2 model. It's actually a model that works well in many situations is this 011, 011. Okay. In this case, it's not that good, but normally it does. And this is called the airline model. Maybe we can take all this back off. So without the seasonal part, it's much better. Sorry, without the COVID part, it's a little bit more precise. And this is usually called the airline model. So this is the portfolio. Our first choice was actually the best one. What about the ensemble? Well, you see, actually, as an ensemble, the first and the second model seems to work slightly better. And actually, the second best model has the airline inside. So ensemble works. Okay, so we finished. I just show you where the regressor go into an ARIMA model, and then I will not do it here because it's I don't think it's a good spent time. But I invite you to try to kind of reproduce what we're doing using this platform using code, R code. But if you like Python better, try with Python. There's the stats library, and inside the stats library you have the ARIMA, the time series, and the ARIMA library. Okay. So an alternative way to write in a short way, in shorter terms, the ARIMA models is this way. So like a mean plus, and here you have all the operators, the non-seasonal, seasonal, MA, the non-seasonal autoregressive parts, and the seasonal autoregressive parts, okay? And this is applied to the white noise. In this case, this is the mean and not the intercept, okay? Because it's like this is a mean zero ARMA process. So if I add the mean, this is a mean new ARMA process. You can check by yourself that this corresponds to the other representation that I gave you. If you just multiply on the left and on the right side by phi small one and the big one, you get the phi here, and then you get phi that multiplies the mu, which is a constant, so you can just leave the p out, and you get that you have the k instead of the mu. Okay, try to do that. This is a very compact way to indicate an ARIMA process, which you will find in mass literature. And actually, so you see that this is just like a time series, which is equal to a mean and then a stationary process. This is the stationary part of the ARIMA process. What about the differences? The difference we put here, okay? However, as I told you, usually if I have the differences, I should take it also, I should apply it also to the other components. I mean, suppose we are taking the first difference, then we are modeling the increment of the time series. So this is the mean increment of the time series, okay? So the role of the mean changes if I take differences, right? How do I solve the problem of regressors? Well, I could write this in a slightly different way. Well, suppose I don't have the differences. I could put the regressors here. So this is like a vector of variables, and this is a vector of coefficients. And then just have the ARMA process. So this is the ARMA part of the process. Okay. So this is the ARMA part. This is the regression, or the X part, the Rmax of the Rmax. What about the differences? So we can see an Rmax process as a regression where the error of the regression are not a white noise, but are just a stationary process, right? If this was a white noise, this would be a standard regression, right? What's the difference? Well, this is an ARMA process. Okay? So you may see Rmax processes just as a regression whose error are not white noise as usually, but they are just a stationary process. Okay, and this is fine. How do you manage the differences? And that's how software may slightly be different. But for example, Python and R in this thing, they agree. So if I, as I showed you now, using the mean, if I take the differences here, the meaning in case of the meaning of the mean changes. If I take the original time series, this is the mean of a time series. If I take the first difference of the time series, this is the mean increment of the time series. If I take two differences of the time series, that's the mean of the mean increment. That would be like the second derivative of the time series. Like, if I don't want the interpretation of the mean or the regressors to change when I take the mean, when I take, sorry, the differences, then I have to apply the same transformations to the regressors, okay? And that's what R and Python do. So they apply the same differences here. Well, actually, they apply it to the X, of course. So I can write it this way. So this is like the regressive coefficient, or maybe I can just turn it the other way. No, well, let's just leave it that way. Of course, this is a vector of regressors. I apply the difference to every single time series of the X vectors, okay? So this is what R and Python do. And that's also why they have this include mean, include drift, or include constant. Okay, because in theory, if you check difference of the mean disappears. Okay, so you have to indicate, because otherwise the mean is treated as exactly as any other regressor. So like a constant regressor. Okay. So I think this is a good idea because it lets you always reason in terms of the level of the time series. Because usually we think about relationship in variables in terms of level. For example, we think that, I don't know, the GDP influences the employment rate. Okay. Actually not. We think the GDP, the growth of the GDP influences the unemployment rate. So in that case, it would be like the difference here, and I wouldn't want a difference here. But anyway, and then there are other complications I don't want to introduce right now, but I will mention later about the behavior, the meaningfulness of a regression of time series on time series. Just to give you a clue, do you think it has any logical rationality if I regress a stationary time series on an integrated time series? So stationary time series stays there. Okay, it goes up and down, but it goes back always to the mean, right? So it stays around the mean. An integrated process tends to move a lot, maybe have strands, produces strands. How can a trending time series explain a stationary time series? Or how can a stationary time series explain a trending one? Okay. Unless there are other ones that are fixing the difference between these behaviors. Okay. So first of all, this is how regressors are made. The dummy variables that we were using there were fit this way. Okay. So doesn't matter what kind of difference we took on the data, the same difference was applied to the dummy variables. So the interpretation of the dummy variables was the level of that date. On that date, the level of the GDP is different. Okay. That's always the interpretation. Okay. Okay. Any questions?
Linear regression of on this
non-linear regression. The model just lets you regress linearly. However, you know that it's strange to say that way, but linear regression includes, as a special case, many nonlinear regressions. You can, of course, transform your X by taking splines basis. I don't know if you ever use splines basis. You can transform X by taking powers, cosine and sines, of course, we're using that. So it's nice because the linear world is actually allows you already many nonlinear generalizations of that.
For example, unknown stationary processes, which require these processes, would be by using linear regression, which could somewhat, for example, about logistic regression, which I know that it's not the point to do, but the logistic function finds the values of the response between 0 and 1.
Yeah, I understand your question. The problem is not really the deterministic parts of the trend. We can always put nonlinear function of the time to fit deterministic trends. Actually, you do it a lot of the time. For example, if you're in advertisement, for example, you have these sigmoid functions because in advertisement, you think if you do too little advertisement, there is almost no effect of your investment. Then it goes up when you're investing enough. But then if you invest too much, then you just, saturated all the channels, and so you're back in not having no more effect. that kind of things, of course, you can by transforming the x variables get. The problem is about the trends is not the deterministic part of the trend, but the stochastic part of the trend. Sorry, a random walk goes up and eventually you can prove that a random walk, if you leave enough time, will pass any threshold. Okay, it will go to infinity eventually. Okay, a stationary variable will always return to the mean. It's also mean reverting. It means that eventually it always it's attracted by the mean. Like people from physics call them attractors. So in that case, a process that always go back to the means means that the mean is an attractor of that process. Okay. How can a regression of something that is attracted to a fixed number to something that eventually goes to infinity have some meaning? It's kind of illogical. Of course, you have to think not of a finite time series. In finite time series, you will always get numbers. But if you think the time series is generated by this kind of processes, then a stationary process cannot be generated, cannot be a linear combination of integrated processes, for example. Well, again, I said something not completely correct. Let's say a stationary process cannot be a constant plus a coefficient times any stationary process, integrated process. Okay, that cannot happen because the integrated property dominates the stationary process, and so there is no way to like take constant time in integrated process and get a stationary process. No, it would be an integrated process. Okay, we will go back to this concept later because I don't want to surcharge you with too many concepts, but they're important because it tells you if you're doing something meaningful or not in your modeling. Okay. In this case, I was thinking mostly about like artificial regressors, like dummies, like trends, like sinusoids. So all function of the time. In this case, all the x are legit. Okay, you cannot get it wrong. Maybe you can get it not significant, but you cannot get it wrong. If you think that also the x is generated by stochastic process, then there is some reasoning that has to be done before modeling. Okay. Other questions? So we see you on Friday.